Hello everyone, in this video we're going to finish talking about 1.7 enzymes. So this is where we left off during class, where we talk about enzymes speeding up chemical reactions. But this picture shows you, or these pictures show you how enzymes can speed up chemical reactions. So enzymes speed up chemical reactions by lowering the activation energy, or the amount of energy needed to begin a reaction. Right? So go ahead and write this down on your notebook as a part of your notes. So what I want you to think about is that when you have a reaction, there's always something that need to be added in order to get the reaction started. So for example, when you burn wood at a campfire, right, or you burn anything really, right, that is a spontaneous reaction. How do you know it's a spontaneous reaction? It happens very easily, right? You know that things can burn easily, right? You also know that reactions that release energy, such as burning, right? You can feel the fire, you can feel the energy coming off of the fire. And reactions that release energy are often spontaneous reactions, meaning that they can happen on their own without a whole lot of extra help, right? But even when you think about burning, things burn easily, but you still need to give that initial spark in order to get the reaction going, right? So that happens to every single type of reaction, whether a reaction overall absorb energy or overall release energy. You still need to add more energy to the reaction first to get things started, okay? So if you look over here, we have reactants and products. We already saw graphs like this during class today, and you can tell that the product energy level is lower than the reactant energy level. How do you know? You will look to the y-axis, right? The y-axis is total energy. The y-axis for the product is lower than it is for the reactants, which means overall during this course of reaction, during time, you lost energy. Okay, so reactant product, we lost energy. However, even though overall there is a loss of energy to allow the products to be formed, you still have to raise the energy of the reactants first before it's able to break down into products or form products. Okay, so that is called the activation energy. It's the difference in energy level between the reactants and the highest level of energy. And then moving on, what enzymes do is that it will lower the activation energy. It will lower the amount of energy needed to get this reaction going. Once it go over this bump, it will keep going and form the product. But getting over this bump is really the difficult part. Okay, so what you see over here on the right side is that now the activation energy is lowered, right? So then the reactant doesn't need as much energy in order to form the products. So I can give you an example. So for example, you know that when a temperature is higher, right, then the reactions happen a lot faster, a lot of the times, right? Because molecules are moving faster, and when they move faster, there's more energy to allow reactions to happen. When you use enzymes, then if a reaction will require you to heat up the reaction itself, you don't have to heat it up as much in order for the products to be formed. Okay, so moving on. When we talk about enzymes, there are also several other factors that we need to think about. Enzymes being specific, for example. What does the word substrate mean, for example? And what are some factors that can affect the rate of reaction, or affect how fast an enzyme can speed up the reaction? So let's take a look. On this page, you can see again that we have the course of reactions. So that's just over time, right? Over time, the reactants are going to form products. You look at the y-axis, you can tell that over time, the products are formed and the products have lower energy levels. So this is an overall releasing of energy, which means this is a spontaneous reaction as well. And then you can see again, activation energy without enzyme is higher than the activation energy with an enzyme. So again, enzymes speed up the chemical reaction by lowering the activation energy. Okay, moving on. Enzymes are specific. What does that mean? Enzymes are like doors, and you got keys to the doors, right? Doors and the keys are specific for each other, meaning that you only have certain keys that can open certain doors. So are enzymes. Enzymes are proteins, right? Enzymes are proteins that can speed up chemical reactions. So proteins have shapes. If you look at the camera, I don't know if I have the camera on. Oh my goodness. Anyway, if you can't see the camera, but you can think about, like, let's say you have a paper airplane, right? If you have a paper airplane, that is a specific shape. How you fold the paper airplane is going to affect how far this paper airplane is going to go, right? So enzymes are proteins with a certain shape. Proteins all have certain shapes, okay? And the reactants that can fit into the enzyme fits at certain parts of the enzyme. So the result is only specific substrates can fit in specific shapes of the enzyme, specific parts of the enzyme, and then form certain products, right? So for example, you can see that on the left side, we have a pretend enzyme. On the right side, we have a pretend enzyme. Only certain molecules can fit in those slots. That's exactly what happens in real life with the enzymes. Being proteins, they have certain shapes, and molecules of certain shapes can fit in it, okay? So that's what we mean by enzymes are specific. Only certain reactants can fit in certain enzymes and form certain products. If you use other reactants for one type of enzyme, it will not work out. All right, on this page, we have something called an enzyme substrate complex. This phrase seems a little complex, but it's really not that difficult, okay? So what we see over here, we have water and carbon dioxide. Those are all our substrates. So what exactly are substrates? Substrates are reactants they're not just any reactant, they're reactants that will interact with enzymes and form products. So what you see over here, we have these two substrates fitting in the enzyme, right? They bind together. Now you form an enzyme substrate complex, okay? So now the enzyme hasn't broken down or forming the products yet. The products are not formed. We just have reactants binding into enzymes. You call that an enzyme substrate complex. And then over time, we can form a product. This is a carbonic acid, right? So in this case, we have two molecules forming into one molecule as our product, okay? The space on an enzyme where the substrate can fit into is called an active site, okay? So there are a few words over here. We have substrate. Those are just the reactants that can fit into an enzyme. We have the word enzyme. You already know that. We have products, right? So the products are released from the enzyme. And then we have the active site where the substrates can bind to. Okay? All right. I'm having a brain fart. Okay, hold on. I'm thinking about something I can't remember. On this page, you can also see that enzymes can be reused, right? This is a whole cycle. This enzyme gets used, you form the product. Now the enzyme is empty again. It can now bind to more substrate, right? So the enzymes can always be reused and they don't get consumed. They are not actually a necessary part of the reaction, but it just speed up the chemical reaction. Okay, so we have substrates and then we have the product. Then we have that active site is available for the next substrate again. All right, this next one again, enzymes are not degraded during a reaction and are reused, right? So you see active site, substrate, binding to enzyme substrate complex is formed. Now we form the product. Now the enzymes can be used again. Lastly, we have something called rates of reaction can be affected by temperature and pH, right? So what we mean by that is the rate of reaction is how fast can the reaction happen during a certain amount of time, right? So for example, if you look at this picture right here, we have temperature on the x-axis, rate of reaction on the y-axis. As the temperature increases, can you see that the rate of the reaction is also increasing, right? So then eventually we get to this high point where you have the highest rate of reaction, which means at this temperature, you can have a ton of the most amount of products being formed from the reactants. Okay, so that's called an optimal temperature, meaning that this is the optimal, like the best temperature where you can form the most amount of products. So the optimal temperature is where you can have the highest rate of reaction, right? So this is the rate of reaction. And then what happens is as you increase the temperature even more, now the rate of reaction actually goes down, right? So if you think about it, if you boil up eggs, for example, those proteins inside the eggs actually break down. They are no longer, right? The chicken egg is no longer a functioning unit. It's not going to form little chicks anymore because you boiled it, right? So this is why when you cook food, right, all the bacteria and all the viruses on the food is not going to be there anymore, right? Your food is now safe to eat because when you're boiling food, that increase of the temperature to really high will break down all the proteins that will allow the bacteria and the viruses to function. Okay, so what you see over here, at high temperature, enzymes would denature. What does that mean? Enzymes have a certain shape, right? We talk about that. Denature means the enzyme will lose its shape. when enzyme loses shape, it's not going to function anymore, right? So if you look over here, the substrate can bind to this active site because the enzyme have a certain shape. But if the enzyme loses that shape, the enzyme's not going to work anymore. You can't have the substrate binding to it and form the products anymore, right? So when an enzyme denature, what it means is that it will lose their unique shape and the ability to function. Different enzymes have different optimal temperature and pH, right? So if you look on the bottom picture, pH is how acidic a solution is, like how much acid there is versus base. That pH is also something that affects the shape of an enzyme. So every single enzyme have an optimal pH where the enzyme shape is optimal, where you can form a ton of product in a certain amount of time. Okay, so what you see over here, how can you find the optimal pH of these three different enzymes? We have pepsin. The x-axis is the pH, right? So at pH 2, pH equals to 2, we have the highest rate of reactions. We say for pepsin, the optimal pH is 2. Okay, and then moving on, we have amylase is another type of enzyme. That optimal pH is 7, right? So that's neutral. As you can see, the y-axis, you always want to look at the x-axis and then you want to look at the y-axis, right? So this is the highest point of the curve, so that is the highest rate of reaction. That gives you the optimal pH, which is pH 7. And then arginase has an optimal pH at about 9.7, okay? You can look at some questions now. Chemical reactions convert what to what? Think about, can you answer that? In non-living system, the presence of a what allows a reaction to proceed very quickly and have a lower what. Yeah, all right, if you are able to answer these questions, that's a good sign. Next week, we're going to have another quiz. Our next test is on the Monday after next week, so about 9 days from now-ish, okay? There are some other questions you can take a look at, but if you can answer all of these questions, so on the PowerPoint slide, there are these questions. If you can answer all those questions, then you'll be able to do really well on the other assessment. And tomorrow we're going to do a lab that will kind of tie everything together. Okay? Have a good one, everybody.